Welcome to today's paper reading. Today's paper is titled, Exploring Advanced Large Language Models with LLMsuite, a free comprehensive recap of techniques, architectures, and practical applications. This paper was published on the AR14 preprint by Giorgio Roffo, a senior research scientist, exploring advanced large language models and their applications. This tutorial discusses the advancements and challenges in the development of large language models, LLMs, such as ChatGPT and Gemini. It highlights inherent limitations including temporal knowledge cutoffs, mathematical inaccuracies, and the generation of incorrect information. To address these issues, the tutorial proposes solutions such as Retrieval Augmented Generation, RAG, Programmated Language Models, PAL, and frameworks like ReAct and LangChain. These techniques enhance LLM performance and reliability, particularly in multi-step reasoning and complex task execution. The tutorial also covers fine-tuning strategies, including instruction fine-tuning, parameter-efficient methods like LoRA, and reinforcement learning from human feedback, RLHF. Additionally, it provides a comprehensive survey of transformer architectures and training techniques for LLMs. The introduction of this paper highlights the significant advancements in the field of natural language processing, NLP, with the advent of large language models, LLMs, like ChatGPT and Gemini. These models are capable of generating text that closely resembles human writing, setting new standards in applications ranging from automated customer support to creative writing. Despite their impressive capabilities, LLMs face several limitations, including temporal knowledge cutoffs, difficulties with complex mathematical computations, and a tendency to produce plausible but incorrect information known as hallucinations. Contemporary research is focusing on addressing these limitations by integrating LLMs with external data sources and applications, such as Retrieval Augmented Generation, RAG, which links LLMs to up-to-date external databases to improve output precision. Additionally, advanced prompting strategies like chain-of-thought prompting are being employed to enhance the reasoning capabilities of LLMs, particularly for tasks requiring multi-step logic. Figure 1 provides an overview of the comprehensive framework used to create an LLM application. At its core, the LLM serves as the primary engine for generating human-like text. The framework integrates tools like Retrieval Augmented Generation, RAG, to enhance the model's capabilities by enabling it to fetch information from external databases. Additionally, techniques such as chain-of-thought, COT, and programmated language models, PAL, are employed to further enhance the reasoning capabilities of the AI system. These components work together to provide a level of functionality and versatility that far exceeds the capabilities of standalone language models. The advanced AI systems like ChatGPT and Gemini are not just large language models, LLMs. They integrate multiple frameworks and capabilities beyond basic LLMs. At their core, LLMs generate human-like text, but tools like Retrieval Augmented Generation, RAG, enhance this by fetching external data. Techniques such as chain-of-thought, COT, and programmated language models, PAL, further improve reasoning. COT breaks down complex queries into manageable steps, while PAL uses external interpreters like Python for calculations. Frameworks like ReAct enable planning and executing strategies for problem-solving. Additionally, systems like GPT-4all and LangChain combine these functionalities into cohesive units, creating a seamless AI experience. These components together provide a level of functionality and versatility far beyond standalone LLMs. Figure 2 illustrates the Retrieval Augmented Generation, RAG framework, which enhances large language models, LLMs, by integrating external data sources. The framework consists of two main components: the parametric component, which uses a pre-trained seek-to-seek model like BART to generate responses based on context from retrieved documents and the query, and the non-parametric component, which employs a dense vector index of documents, such as Wikipedia, with a neural retriever like DPR to fetch relevant documents based on the query. The workflow involves three steps: query input, where the retriever processes the input query to find relevant context; document retrieval, where the retriever computes vector representations of the query and documents, retrieving the most relevant ones using techniques like maximum inner product search; MIPS, and sequence generation, where the retrieved documents, along with the original query, are fed into the Seek generator to produce the output text by integrating information from both sources. The Retrieval Augmented Generation (RAG) framework addresses significant limitations of large language models, LLMs, such as ChatGPT and Gemini. These models face issues like outdated knowledge due to temporal cutoffs, errors in complex mathematical tasks, and the generation of plausible but incorrect information, known as hallucinations. RAG integrates external data sources and applications at inference time to overcome these challenges. It updates the model's knowledge base and improves accuracy without the need for costly retraining. The framework includes a retriever component that encodes user queries and searches external data sources for relevant information. This augmented query is then processed by the LLM to produce more accurate responses. For instance, in legal applications, RAG can enhance document retrieval during discovery phases. This approach not only updates the model's knowledge but also mitigates hallucinations by grounding responses in external data. Implementing RAG requires managing context window limitations and efficient data retrieval techniques like vector stores for rapid semantic searches. Large language models, LLMs, are being integrated with external applications to perform complex tasks. This integration allows LLMs to interact with the broader world based on user inputs, acting as a reasoning engine. However, LLMs often face challenges in complex reasoning, especially in multi-step tasks or mathematical problems. To address these issues, researchers use chain-of-thought prompting to break down problems into intermediate steps. Despite improvements, LLMs still struggle with precise calculations. To overcome this, the Programmated Language Model (PAL) framework pairs an LLM with a Python interpreter to perform accurate computations. PAL generates executable Python scripts based on reasoning steps, ensuring the accuracy of calculations. This framework significantly enhances the capability of LLMs to handle complex computations accurately. Figure 3 illustrates the pipeline of the Programmated Language Model (PAL), showcasing how user questions are integrated through PAL prompt templates and Python interpreters. This framework significantly enhances the accuracy of large language models, LLMs, in performing mathematical computations by generating executable Python scripts based on reasoning steps. The Python interpreter then executes these scripts to ensure precise calculations, demonstrating PAL's effectiveness in complex problem-solving tasks. The ReAct framework, developed by researchers from Princeton University and Google, stands for Reasoning Plus Acting. It enhances large language models, LLMs, by combining reasoning with actionable outputs, enabling them to interact with external tools and environments. This framework is particularly effective in knowledge-intensive tasks like multi-hop question answering and decision-making in simulated environments. ReAct's prompting strategy involves a thought-action-observation cycle, where the model generates reasoning traces and takes actions to gather information. These actions are predefined, such as searching Wikipedia or looking up specific keywords, ensuring the model operates within feasible steps. This approach has been exemplified by applications like Microsoft's Office 365 Copilot, where LLMs generate verbal reasoning traces and actions to enhance decision-making processes. LangChain is an open-source framework designed to streamline the development of applications based on large language models, LLMs. It provides tools and abstractions to enhance the customization, accuracy, and relevancy of the information generated by LLMs. Key components include prompt templates, memory storage, and tools for various tasks such as API calls and external dataset access. LangChain is particularly important for repurposing LLMs for domain-specific applications without retraining or fine-tuning. It allows development teams to build complex applications that reference proprietary information to augment model responses. For example, LangChain can be used to create Retrieval Augmented Generation (RAG) workflows that introduce new information to the language model during prompting, reducing model hallucination and improving response accuracy. By abstracting the complexity of data source integrations and prompt refining, LangChain simplifies AI development, allowing developers to build complex applications quickly. The transformer architecture consists of two main components, the encoder and the decoder. Each component includes a self-attention mechanism followed by a feed-forward neural network. The self-attention mechanism allows the model to consider the relevance of each word in a sentence to every other word, enabling it to capture complex dependencies. This mechanism is computed using matrices Q, K, and V. Transformers also utilize multi-headed self-attention, which projects the input into multiple subspaces, allowing the model to capture various aspects of token relationships. Positional encoding is added to retain information about the order of tokens. Notable transformer-based models include BERT for deep understanding tasks, BART and T5 for sequence-to-sequence tasks, and the GPT family for text generation tasks. Figure 4 provides a detailed comparison of the Llama and GPT-3 architectures, focusing on their unique components and functionalities. The Llama architecture is depicted on the left, highlighting its use of grouped multi-query attention for efficient processing, along with rotary positional encodings and RMS normalization in feed-forward layers. On the right, the GPT-3 architecture is shown, emphasizing its deep 96-layer structure with masked multi-self-attention and layer normalization. A significant insight is the application of token embedding rotation in Llama, which helps in capturing contextual word roles effectively. Scaling model training across multiple GPUs is crucial for handling large models that exceed the memory capacity of a single GPU. For models that fit on one GPU, using multiple GPUs can significantly speed up training. PyTorch's distributed data parallel, DDP, is commonly used to distribute large datasets across GPUs, enabling parallel processing. However, when models exceed the memory capacity of a single GPU, techniques like fully sharded data parallel, FSDP, become necessary. FSDP, inspired by Microsoft's Zero Optimizer, distributes model states across GPUs without redundancy, reducing memory usage. This method involves sharding optimizer states, gradients, and model parameters across GPUs. While FSDP reduces memory usage, it increases communication overhead, requiring a trade-off between performance and memory. For smaller models, FSDP and DDP perform comparably, but for larger models, FSDP is more effective, especially with 16-bit precision. Understanding these techniques is essential for optimizing the training of large language models. The development of 1-bit large language models, such as BitNet-B 1.58, has introduced significant advancements in model training efficiency and performance. BitNet-B 1.58 quantizes model weights to ternary values, reducing memory footprint, latency, and energy consumption while maintaining high performance. Specifically, BitNet-B 1.58 uses 3.55 times less GPU memory, achieves 2.71 times faster inference, and offers 8.9 times higher throughput compared to traditional 16-bit floating-point models. Additionally, it is 71.4 times more energy efficient in matrix multiplication operations due to the use of integer addition instead of floating-point operations. These improvements make 1-bit LLMs like BitNet-B 1.58 a promising direction for scalable and sustainable AI, potentially leading to the development of specialized hardware optimized for 1-bit computations. Figure 5 provides an overview of the 3 stages of zero optimization. Stage 1 focuses on sharding optimizer states, reducing memory usage by up to 4 times. Stage 2 adds sharding of gradients, achieving an 8-fold memory reduction. Stage 3 involves sharding all model components, offering a linear reduction in memory usage proportional to the number of GPUs. This figure is crucial for understanding how zero optimizes memory usage in large-scale model training. In fine-tuning models, it is essential to employ multitask settings and diverse datasets to ensure robust performance across various tasks. References to available datasets are crucial for selecting appropriate data for specific fine-tuning needs. Table 1 provides an overview of commonly used natural language processing datasets, including their type, citation, and a brief description. This table serves as a comprehensive resource, helping to understand the scope and capabilities of different data sources in the field of natural language processing. The focus of this section is on improving the performance of large language models through fine-tuning, enhancing their capabilities and the scope of their data sources. Fine-tuning is a critical method for enhancing the performance of large language models, LLMs, for specific tasks. This process involves supervised learning, where the model's weights are updated using prompt completion pairs. A particularly effective approach is instruction fine-tuning, which uses examples that explicitly show the desired responses to specific instructions. However, fine-tuning can be resource-intensive, requiring substantial memory and compute capacity. Advances in memory optimization and parallel computing strategies help mitigate these demands. One significant challenge in fine-tuning is catastrophic forgetting, where the model's performance on previously learned tasks deteriorates. To address this, multitask fine-tuning and parameter-efficient fine-tuning, PFT, are employed. Multitask fine-tuning involves training on multiple tasks simultaneously, while PFT preserves most of the pre-trained weights by training only a few task-specific adapter layers, thereby maintaining multitask performance. Table 1 provides a comprehensive overview of datasets and benchmarks commonly used in natural language processing tasks. It includes a variety of benchmarks such as GLUE, Superglue, MMLU, Big Bench, Helm, and Gemini, which are designed to evaluate the performance of language models across different tasks. Additionally, it lists specific datasets like COLA, SST2, MRPC, STS, QQP, MNLI, QNLI, RT, and WNLI, which are used for tasks ranging from sentiment analysis to textual entailment. The table also highlights datasets like COT, Muffin, Natural Instructions v2, MGSM, and BBH, which are crucial for fine-tuning models on specific tasks and evaluating their generalization capabilities. This overview serves as a valuable resource for researchers and practitioners in selecting appropriate data for their NLP projects. Multitask fine-tuning enhances model performance across multiple tasks by training on datasets that include various tasks such as summarization and entity recognition. This method helps in mitigating the issue of catastrophic forgetting. However, it is data-intensive, often requiring between 50,000 to 100,000 examples. The FLAN models, including FLAN T5, are examples of successful multitask fine-tuning, having been trained on a large and diverse set of 473 datasets across 146 task categories. For specific applications, additional fine-tuning on domain-specific datasets, such as dialogue sum for customer service interactions, can further improve the model's performance, making the summaries more accurate and relevant. Training large language models is a resource-intensive task. Full fine-tuning requires substantial computational and memory resources, including storage for optimizer states, gradients, and activations. Parameter-efficient fine-tuning, PFT, offers a solution by updating only a subset of parameters, significantly reducing the memory footprint. PFT methods include selective tuning, reparameterization techniques like low-rank adaptation, LoRA, and additive methods such as adapters and soft prompts. LoRA introduces low-rank decompositions of weight matrices, reducing the number of parameters that need training, making it more efficient. LoRA is a reparameterization technique that freezes the original large language model, LLM, weights and injects low-rank decomposition matrices alongside them. This approach significantly reduces the number of trainable parameters by creating small matrices whose product approximates the original weights. Specifically, a large weight matrix W is an element of RD times K is approximated by the product of two smaller matrices A is an element of RD times R and B is an element of RR times K, whereas much smaller than the minimum of D and K. During fine-tuning, only the matrices A and B are updated, while W remains fixed, reducing the number of parameters to R times D plus K, which is much smaller than D times K. For instance, with D equals 512, K equals 64, and R equals 8, the reduction in parameters is substantial, from 32,768 to 4,608. Despite this reduction, models fine-tuned with LoRA maintain high performance. The technique leverages the fact that the essential information in the weight matrices can often be captured with a lower rank approximation, thus preserving the model's ability to perform well on downstream tasks. Selecting the appropriate rank for LoRA matrices is crucial for balancing parameter reduction and model performance. Research suggests that ranks in the range of 4 to 32 offer a good trade-off, with minimal performance loss beyond a rank of 16. Figure 6 provides an overview of the low-rank adaptation, LoRA, technique, illustrating how low-rank matrices are injected to approximate the original weights of a large language model, LLM. During the fine-tuning process, only the matrices A and B are updated, while the original weight matrix W remains fixed. This method significantly reduces the number of trainable parameters from D times K to R times D plus K, whereas much smaller than the minimum of D and K. For instance, with D equals 512, K equals 64, and R equals 8, the reduction in parameters is substantial, from 32,768 to 4,608. Despite the reduction, models fine-tuned with LoRA maintain high performance, as the technique leverages the fact that the essential information in the weight matrices can often be captured with a lower rank approximation. Figure 7 provides an overview of the concept of soft prompts and prompt tuning. It illustrates how trainable tokens are added to the input text, which are then represented as additional embedding vectors. These soft prompts are prepended to the input text embedding vectors and are adjusted during training while keeping the model weights fixed. This method is highly parameter efficient, involving only a small number of additional parameters compared to full fine-tuning, making it a viable alternative especially when computational resources are constrained. Prompt tuning involves the addition of trainable tokens, known as soft prompts, to the input text. These soft prompts are virtual tokens within the continuous embedding space and are prepended to the input text embedding vectors. During training, only these soft prompts are adjusted while keeping the model weights fixed. This approach is highly parameter efficient, as it only involves a small number of additional parameters compared to full fine-tuning. For example, tuning a 5-token prompt for a model with an embedding dimension of 2048 only adds 10,240 parameters. The effectiveness of prompt tuning varies with model size. It underperforms full fine-tuning for smaller models but becomes competitive as model size increases, particularly for models with around 10 billion parameters. This efficiency and scalability make prompt tuning a viable alternative to full fine-tuning, especially when computational resources are constrained. The comparative analysis between LoRA and prompt tuning methods reveals their distinct strengths in parameter-efficient fine-tuning. LoRA excels in scenarios requiring significant parameter reduction without performance loss, thanks to its matrix factorization technique. This makes it ideal for fine-tuning large models on hardware with limited memory. Conversely, prompt tuning uses soft prompts to condition pre-trained models for specific tasks with minimal additional parameters, making it highly scalable and effective for large models. Future research should explore hybrid approaches combining LoRa's parameter reduction with prompt tuning's task-specific enhancements. Additionally, developing adaptive PFT methods that dynamically adjust based on task complexity could further optimize fine-tuning processes. These advancements are crucial for deploying large models efficiently across various domains. In this section, we compare two advanced methodologies for enhancing large language models: reinforcement learning from human feedback, RLHF, and reinforced self-training, REST. RLHF involves fine-tuning models using human feedback, training a reward model, and optimizing the policy with algorithms like PPO and A2C. On the other hand, REST introduces a two-loop structure, separating data generation and policy improvement, which enhances efficiency and reduces computational costs. A comparative analysis shows that while RLHF offers high-quality improvements through direct human feedback, it comes with higher computational costs and risks of reward hacking. REST, with its offline RL approach, provides a more stable and efficient alternative, particularly suited for large-scale applications. Both methods have unique strengths and weaknesses, and future research may explore hybrid approaches to leverage their respective advantages. The Proximal Policy Optimization (PPO) algorithm is divided into two main phases. In Phase 1, the Large Language Model, LLM, completes tasks based on given prompts, with responses evaluated against a reward model that captures human preferences. Rewards are based on criteria like helpfulness and honesty. In Phase 2, the LLM's weights are updated within a trust region to maintain policy stability. The PPO objective function includes a policy loss to maximize rewards, a value function loss to estimate rewards, and an entropy loss to balance creativity. This method aligns LLMs closely with human preferences and is widely used in reinforcement learning with human feedback, RLHF. While other techniques like Q-learning are also explored, PPO's balance of complexity and performance makes it a prevalent choice. Ongoing research includes exploring new methods like direct preference optimization, DPO. The paper concludes by highlighting the limitations of large language models, LLMs, such as outdated knowledge, difficulty in complex computations, and generating incorrect information. To address these issues, several innovative techniques have been introduced. Retrieval Augmented Generation, RAG, connects LLMs to current external databases, enhancing their accuracy and relevance. Program-Aided Language Models, PAL, use external code interpreters for precise computations, broadening LLM capabilities. The LangChain framework simplifies the integration of LLMs with external data sources, enabling efficient development of domain-specific applications. Additionally, fine-tuning strategies like instruction fine-tuning, multitask fine-tuning, and parameter-efficient methods such as low-rank adaptation, LoRA, and prompt tuning are discussed to mitigate catastrophic forgetting and improve performance. Thank you for watching.